Good evening, everybody. I'm Gabriel Motzkin. I'm the director of the Van Leer Jerusalem Institute, and it is my especial honor and pleasure to preside at this event of the Oscar van Leer, the 10th Oscar van Leer Lecture. This is a custom that we adopted here at Van Leer several years ago to honor a distinguished contributor to science and or society. And this year, given the significant and dramatic discovery that has occurred in our understanding of the world, we thought it proper to honor somebody who was personally involved in this discovery. Human beings have spent a long time trying to decipher the meaning of the world around them, and we are lucky that we have a rich internal world of associations, and that in this world we can project something like invisible forces or invisible particles of which we know not. Now, the first and earliest members of our species did this through magic or through seeing unseen forces in the world around them, and in a deep sense, they were right. They only didn't understand the rules according to which these forces worked, and they thought that these forces could be propitiated or could work in some irrational ways, and so, because they could not predict the future, they thought to influence it. Now, since that time, we have embarked on first the knowledge of society and understanding other people's minds, the truth and deceit which adhere to all human conduct, and which were essential for our creation of a language in which we could invent theories and communicate them to others. In our world today, we are lucky, for one thing alone, that we have the language and that we can distill it into mathematical theories that apparently give us the laws of the universe. Now, as we all know, much has been made in the last year that most of the universe, dark matter and dark energy, are as yet unknown. But even the fact that we can predict the movement of particles, that of the few particles we can see, of the atomic or baryonic world, means a great deal to us. So we're very happy to be part and to listen to be part of this world and to listen to something about how this discovery was made. Now, let me explain to you, we will hear all about the Higgs boson, but it's obvious to you that the Higgs boson was an essential part of the fundamental theory of particle physics, and that without it, we would still be like string theory is in worlds of mathematical speculation without empirical proof. Our honoree this year is Professor Eilam Gross, who is Professor of Particle Physics at the Weizmann Institute of Science, who was born in Tel Aviv and studied for his first degree at the Hebrew University up the hill, and he graduated with special honors, and then acquired his further degrees from the Weizmann Institute of Science and did his postdoctorate at CERN. CERN is the European Laboratory for Nuclear Research, and it's located right at the border between France and Switzerland. If you go out to Geneva beyond the airport, you'll find it. In 1993, he returned to the Weizmann Institute and continued the search for the Higgs boson, which he had joined as a student. A year ago, he became the Atlas, you'll have to explain to us what that is, Higgs co-convener, and led the group at the time of the discovery of the Higgs boson at CERN. And so it's a special privilege for us to hear about this from the person who did it. And without further ado, I invite Professor Eilam Gross to give his lecture. At the end, please stay in your seats, because at that point we will award him the Oscar van Leer Medal. So now Professor Eilam Gross will address us on the subject, the quest for the God particle. Please, Eilam.
Thank you for this very kind word and the invitation. Actually, your introduction was more scientific than my talk, in a way. So I called my lecture Soldier of Higgs, and I think that you will understand that the meaning is that actually there were about 6,000 people, at least, who should get the Nobel Prize for the discovery of the Higgs boson. 6,000, no less. So in July 4th, 2012, it was not only America's United States Independence Day, but also the announcement of the discovery of the existence of the so-called God particle at CERN, the Central European Research Nuclear. And the newspapers were completely crazy, as you see here, or here, Eureka, that's what Archimedes called when he discovered his law, according to the legend. Or here, the book of secrets of the universe reveals its secrets. Or here, I cannot read, it's too small the letters for me, but the particle of God exists, Historia in the making, or something like that. So, Higgs boson, what is the Higgs boson? So, you know, people hear my lectures, and I gave a lot of lectures, and God particle, Higgs boson, so I can talk for, like now, 45, 50 minutes, or 1 hour and a half, or 3 hours. There will always be the guy at the end, and then two guys will ask me, what can you do with it? What application does it have? Is it worth $1 billion investing in it? And I'm always getting very nervous and angry when I hear these questions. And it goes together with the beautiful things that you said, actually, in favor of answering this. So I want to link the story of the discovery of the Higgs boson with what is called basic science and what is called curiosity-driven science, which is what we do for many, many tens of years in the search for the Higgs boson. So curiosity-driven science, not like applied physics, it has no limits. You don't know what you will find. It's actually, it can compete only with imagination. As you know, Einstein has already said that imagination is more important than knowledge, which means that curiosity-driven science is the thing that advances knowledge. No other science can advance knowledge. So I found a way, so you will always remember what I said by writing E equals mc squared, E equals mind times curiosity squared. So remember that, okay? So basic science, or basic science is curiosity-driven science, is trying to understand really the fundamentals without aiming to do anything with it, just to understand, because we are human beings, we think, we want to understand. So it always takes us forward. I mean, had we not have basic science, we would still go with chariots or something like this, and now we have missiles and, you know, we can go to the moon and we can go to Mars. Or we could still be in the Middle Ages, we could still light the room with candles, but now we invented the WWW as a result of the search for the Higgs boson. It's not the subject of this lecture, but a byproduct of this curiosity-driven science, like search for the Higgs boson, brought us the WWW, the World Wide Web. So every time you type www, you remember it came because of the Higgs boson. So curiosity brings you into knowledge. And an example, a classical example, is the discovery of the electron, which was made in 1895 by Thomson. And everybody criticized him, like you said, why do you look for a particle that nobody sees? You know, what is this thing that you look for a particle that nobody sees? And by the way, people 100 years ago, or a little bit more, 110 years ago, in the beginning of the 20th century, people still doubted the existence of atoms. You don't see them. So Einstein had to write one of his famous papers to prove by Brown and Motzkin or whatever that atoms exist. So Thomson was looking for this thing that nobody sees, and he was criticized, and he discovered it. And then the legend tells that when they raised the glass of champagne to celebrate the discovery of the electron, he said, to the useless electron. And today we know what the useless electron did. So when you do curiosity-driven science, you never know what results will come practically. And the scientist doesn't really care. But it takes sometimes tens of years, hundreds of years till you know what to do with it. But when Thomson did his experiment, I mean, you can buy the instrument, this vacuum tube. This is actually the cathode ray tube, the same tube that's used in the old televisions, if you like, the huge television that we used to have. So when Thomson did his lecture, the experiment costed $100. And today, such an experiment at that level costs, nobody knows, between $2 to $8 billion. Depends if you count the salaries of the thousands of scientists involved or you don't count, but it's a lot of money. And of course, you cannot raise it from your own pocket, from your salary, or not even from your budget or whatever as a scientist. This is what is called big science. Lots of people are involved in big science. Actually, there are two collaborations at CERN, looking for the Higgs boson. One of them is called CMS, the other is called Atlas. And Atlas collaboration, these are the countries where the members of the Atlas collaboration come from. So isn't it amazing? It's more than half of the world. And that's the only way to raise such an experiment, to use experiments. So you understand why you need a lot of people to make such a discovery, to make such a search even. I mean, the Atlas collaboration has 3,000 physicists, and I call them 3,000 physicists driven by curiosity. And I will go back to this picture to tell you who are the people that you see here, in a way. So let's go to the story behind the discovery of the God particle Higgs boson. Curiosity, what are we made of? That's a question driven by curiosity. Why do we exist? I'm sure that every intelligent person asks himself this question. I'm not sure that the dog asks itself this question. How has it all begun? It's another question that we start to ask it normally at the age of some. I had some people coming, some children coming to my popular lectures at the age of 7, 8 to ask these questions, but normally when you're an adult, young adult, you start to ask these questions. Now it turns out that a large part of the answer lies in what we call mass. Mass, just mass. Weight is made of mass. So in order to explain to you the origin of mass, I collaborated with a great woman who made some great sketches for me. So all the sketches in this lecture, I thank Edith for them from Switzerland. I just met her by a common friend, Yariv, and she did great work for me. So let's start with the universe in the beginning when it's empty. Nothing exists. I mean, in the beginning there was nothing, absolutely nothing. And in this nothingness, particles would move at the speed of light. So for me, a particle, I'm talking about fundamental particles, but to make it clear to you, I'll give you analogies. So this woman here, she can move at the speed of light, you see? She can move very fast. Okay, but then, when the world is created, a field is created, which is what we call the Higgs field. It's like a water in this aquarium of the universe. And then particles in this ether, this modern ether, the Higgs field, when they move in the field, they interact with the content, with the field. They interact with the field. Some people interact strong with the field, and it's hard for them to move, so they gain mass, and they become massive. Other particles, not necessarily all particles are point-like. It's not about the size. Other particles have no interaction with the field or very weak interaction with the field, so they move more freely. They interact less with the field, so they have less mass. They are actually very, very light. So if we go back to our analogy, now our woman find it hard to move, so it makes her feel a bit massive, okay? But the fish, even though it's the same size, can move freely because it has less interaction with the water. So in our analogy, the woman represents a fundamental particle that is become massive. And the fish represents a fundamental particle that is very, very light. So it's the field that gives mass to the particle, the field, the Higgs field. In analogy, the aquarium is the universe, the water is the Higgs field, the ether, the Higgs field, and the woman and the fish are fundamental particles. The woman interacts a lot with the content, with the ether, with the Higgs, and therefore she gains a lot of mass, and the fish hardly interacts, and it can move fast. It gains very, very low mass. This Higgs field was created something like 10th of a billionth of a second after the Big Bang, which means 14 billion years ago. I want to talk a little bit about what we are made of. So the atom, everybody knows it's a nucleus surrounded by electrons. We don't even know where the electrons are. The nucleus is made from proton and neutron, and these are not yet fundamental particles, and these protons and neutrons are made from quarks. But you have to remember that the atom is mostly empty. If I zoom the atom and enlarge it so it has the size of a football field, the electron would not be seen. I just put an observer here, so you will see something, but you wouldn't see the electron, and the nucleus will be the size of a bee or something like this. So if you look at the hydrogen atom, one could ask the question, how big is the hydrogen atom? Is it huge? Is it small? Did you ever ask yourself the question? What does it matter how big is the hydrogen atom? Who cares? Could it be smaller? Could it be bigger? Now comes quantum mechanics into the game and what is called the uncertainty principle, which means that if a particle is heavy, then it's well located. If it's light, you cannot locate it. It's anywhere. So that's the story. Since the nucleus is about, at least the proton is 2 times heavier than the electron, so the nucleus is kind of still in its place, standing still. But the electron moves around. If the electron is very, very light, maybe you got it, the atom will be bigger or smaller? Bigger, because the electron will be anywhere, so you can't even trace it. So it's anywhere, so the atom is huge. If the electron would be very, very heavy, then you can locate it. It's localized, and then the atom would be much, much smaller. So the thing goes like this. Had the electron been lighter, what would have happened is that water would evaporate in a much lower temperature. So we would live in a world without water, a dune world. Everything would ionize. It will be very easy. Every photon that will hit air will remove an electron from there because the atom will be so big and so far from the nucleus that nothing will connect it to the nucleus, so we'll be completely disintegrated. We wouldn't be here. Chemistry wouldn't be what we know. And the electrons being heavier than what they are, then chemistry again wouldn't be the chemistry that we know. Atoms would be much, much smaller. There'll be a competition between the nuclear force and the electric force, and no galaxies would be formed, and we wouldn't be here. So it's the miracle of all miracles. The miracle of all miracles that no life would have been existed if the electron would have been lighter or heavier. Now you can ask yourself, how come that the electron has exactly the mass that enables our existence? This is the mystery of all mysteries. One answer could be, God. So that's why I think that the name that they gave to the Higgs field that requires mass to all fundamental particles is poetic, and nobody meant to say that it replaces God. It does not compete with God, but it plays some role of existence. So that's why the name God particle to the Higgs makes a bit of a sense, even though it's a poetic name, and we call it still the Higgs boson. But the Higgs boson is responsible for the mass of all fundamental particles which enable our existence. In 1964, Peter Higgs, you see him here in 2 versions. You see the 1964 version and the 2010 version of Mr. Higgs. In 1964, he predicted the existence of a field responsible for giving mass to all fundamental particles in nature through the process of what he calls spontaneous symmetry breaking. For this, him and Francois Engler, and Robert Brout, who died about a year and a half ago, got the Wolf Prize a few years ago. The idea is now that there is this Higgs field, but it was still theory. It was like Gabi said, it was theory and it was mathematics. You still have to prove that it exists. How do you prove that the Higgs field exists? By investing energy in the Higgs field, the same energy that exists in the universe, in the creation of the universe, like 14 billion years ago. By investing this energy density in the field, you can create the Higgs particle out of the field and kind of catch it, discover it. You have to create the particle, and then you prove that the field exists. Fields are actually enable us to create particles. So you have to invest energy in the field to create the Higgs field and then see it, observe it. So Higgs was the first one, or one of the first one, to predict the existence of such a particle through the mechanism of spontaneous symmetry breaking. And that's why they got the Wolf Prize. And this is actually why probably it will be 2 of the 3, because Brout is dead by now. At least Engler and Higgs will probably get the Nobel Prize next year for both the spontaneous symmetry breaking mechanism and the prediction of the Higgs particle. The spontaneous symmetry breaking mechanism is too hard to explain in the time that I have, but it's a cute thing. Why is it called symmetry breaking? You see this Mexican hat, it has kind of a perfect circular symmetry. Now if I let, the universe is represented by the little person. And if I let the universe find some minimum energy state, it will find it at the bottom of the hat. But if you look at it, you lost the circular symmetry of each hat. But still, if you look at the picture, it looks very symmetric. On the other hand, if they will all fall to the same place, the symmetry of each hat is broken. But now you see that something happened. There is a preferred side here, and the universe chose something, and the symmetry is broken. This is called spontaneous symmetry breaking. The hat is still symmetric, but the universe itself is represented by the little person is not symmetric anymore. That were the two most complicated slides in my presentation. But there is a much simpler way to explain where were we about a year ago. We had a standard model with all particles predicted and found, like the electron, the heavier electron, which is called the muon, quarks like up, down, other quarks have funny name, charm, strange, top, bottom. We had the force carriers like the photon that carries the electromagnetic force, the W and the Z which carry the weak force, the gluons carry the strong nuclear force. All of them were discovered, and there were not that many. You can count them as 17 particles, which you can create a puzzle with them, a puzzle the children can play with 17 pieces. So mommy bought this puzzle to a 5-year-old child and gave him to play with it. He starts to cry. She goes into the room and she sees that he doesn't manage to complete the puzzle. He's very, very frustrated because there's a missing piece here. She goes into the room, and of course the child blames the mother. What did you do to me? What did you buy to me? It's broken. It doesn't work. She tries to make the pieces again. Nothing works. So she says, okay, let's call the manufacturer and get an extra spare piece. She goes to the box. She sees that the piece should be the red one in the puzzle, which is called Higgs. And then she looks who is the manufacturer. And she sees on the box, made by God, 13.7 billion years after the Big Bang. I mean, this is, how do you go 13.7 billion years backward in time? I mean, you won't answer the phone for sure. I mean, what do you do? What do you do? So the only way to do it is to take scissors and take the same material the world was made of in the Big Bang and make the piece. Just make the piece all over again. And that's what we do at CERN. We first build an accelerator that will give us the energy density that existed in the Big Bang by collisions of two protons. And then to see what comes after the collision, we put an eye to watch. And the eye is a huge detector, 50 meters by 25 meters. And that's why you need 6,000 physicists to build such a detector. Each one of them is important. Each screw is important. And that's a hell of a job to build such an eye. And why do I call it an eye? So Edith helped me to show to you what does it mean an eye. Why is this detector an eye? Because you are all detectors. You are photon detectors. You are very simple, and I'll explain why you are primitive photon detectors. But let me see, what does it mean that you see me or you see this frog here, okay? Because when light hits this frog, it goes back to your eye. Your eye absorbs the photon, interacts with it, sends electric signals to the brain, and the brain creates a visual of the object. So, do you see the frog or do you see a visual of the frog? You see a visual. When you look at me, you see a visual of me that was created in your brain. You're like a camera, you take a picture of me, and you create a visual in real time of me. But your eye is a very, very primitive detector because it can only detect and react to photons in the visible light spectrum. It cannot interact with infrared, ultraviolet, hadrons, etc. It cannot interact with other particles. We need a much more sophisticated eye to see the Higgs boson. And that's why we build the bionic eye, and I'll show you how we do it. So we have a tunnel, 27 kilometers underneath Geneva and the towns that are adjacent to Geneva in France there, 27 kilometers. In this kilometer, we accelerate protons at the speed of light. These protons collide, and in the collision point, they collide with energies with the same density as about a billionth of a second after the Big Bang, or tenth of a billionth of a second, at the same time that the Higgs field was created. And at this point we want to look. So if we put I want to see the human being that will agree to stand there, but that won't be enough, this eye. We need the bionic eye that is much more sophisticated than the human eye. This bionic eye absorbs the collision products, which will interact with the electronics of this bionic eye, and the electronic will send signal to the bionic brain. What is the bionic brain? Computer, right. And the computer will create a visual. So now you tell me, do we see the Higgs or we don't see the Higgs? You see the Higgs just like you see me. So when you go to the Atlas, the collaboration control room, above the ground, 150 meters below is the accelerator and the collision point, you see this painting by an American, and it's a beautiful painting of the detector and the collision. It is still much, much smaller than the detector itself. Now, how do we detect the Higgs boson? The Higgs boson has many, many phases. It doesn't really live. It decays immediately when it's created. And we observe it only via its decay products. So, for example, this is a photograph, if you like. I could put it in brackets, but I believe this is a photograph of a Higgs boson decaying into 2 photons. It's no less a photograph than taking a photograph with a camera. And this is a photograph of a Higgs boson decaying into electrons and muons. How do we know it's a Higgs boson? We don't really know it's a Higgs boson. There are other particles that decay like the Higgs boson, but this is a good Higgs boson candidate. And I'll explain to you in a second how we do it. You need 3,000 physicists, I would call them curiosity-driven scientists, physicists, to build the detector, build the electronics, analyze the electronics, and then sit down, analyze the computer results, data, and deduce whatever they deduce. So just to show you that there are lots of people here, I just took almost random port here and I increased it so you see who is there. So you can see, this is, by the way, the celebration of the discovery of the Higgs boson. So most 3,000 people, I don't think there are 3,000 here, but many, many people came because everybody feels belong. So you see me here, one Higgs soldier. You see also Fabiota Gianotte, who is the spokesperson of the experiment, just like anybody else. You see also Kevin, who's a physics convener, physics coordinator, who takes care of all the physics of the experiment, because we do many, many more things but Higgs. But you see other people, each one had a role and each one is important. Alex, who is statistics convener, and Lauren, who is a colleague from Weizmann doing data acquisition with electronics, or Herman, who is a student doing great things, or Peter, another postdoc or student, or Swagato, another postdoc from India. They all come from many, many different countries. And you can spot also a small group of visually Higgs soldiers, which are a few tens of people coming from Tel Aviv University, Technion, and Weizmann. The head of the Israeli group is Professor Guillaume Mickenberg. They built this 1% but very important piece of the detector, which are the two, they built many more than two, which are the big wheels that you see here, which are what we call muon chambers that help us to decide which collisions could turn out to be Higgs bosons. Because you cannot write on every collision. If you write every collision, you have billion collisions per second, you won't be able to analyze your data in a lifetime. In order to be able to detect the Higgs boson, you need to filter 99.99999% of the data and write down only suspicious, only usual suspects. And this detector of Weizmann, Tel Aviv, and the Technion is a detector that enables us, amongst there are other detectors like this is one of them, that enable us to do what we call trigger and tell us which events are important to write down. The Israeli did it together with the Japanese and the Chinese. And this is the group of Israel, the Japanese, the Chinese, who built this muon trigger system. And George Mickenberg was the leader of this project. So how do 3,000 physicists harmonize the search for one tiny particle? So there's the Atlas collaboration with 3,000 members. There's a spokesperson under which there is a technical coordinator. You have to build a detector. You have to see that it's working. And that's more important than even the analysis, because you cannot do analysis if technology doesn't work. And then after the technology works, and only after technology works, you have the physics coordinator. And under the physics coordinator, there are lots of groups, because you do a lot of physics besides the Higgs boson search. But the Higgs group is actually made of about 600 registered members. And on top of the Higgs group is the Higgs convener. There are two Higgs conveners. It was at that time of discovery, it was me and Sandra Horvath. And the Higgs group itself, as you see, is made of 7 subgroups. Because the Higgs can, when it's detected, it immediately dies and decays. It can decay to photons, to force carriers of the electroweak force like ZZ, WW, to heavy electrons, which called taus, to heavy quarks, which called B, and you need to combine all the results together. So there are a lot of subgroups under the big Higgs group, and the Higgs group is led by the Higgs convener, and the subgroups are led by the subgroup conveners. So for me, since I started 25 years ago, the dream of the lifetime would have been to be a Higgs convener. So when Atlas started to work in 2000, every year I dreamt to be a Higgs convener. I tried to do it and never made it. 2001, 2, 3, I never made it. Then we started to take data. 2010, I was not appointed to Higgs convener. And then I was offered to start and work a little bit on search for dark matter in Gran Sasso in Italy. This collaboration had not 3,000 people by 30 people. So they can all take one picture, small picture, and you see all of them. And you can become quickly visible. Everybody knows you. And I was very happy. And I said, okay, maybe I was not made up to become a Higgs convener. So I kind of started to work with this collaboration. And just as I almost made up my mind to give up the wish to become a Higgs convener, a telephone call came from CERN in the 26th of April 2011. I got the telephone to say, would you like to be Atlas Higgs convener? I had a problem. I lost a bit of the drive because my brother got very ill at that time. He died about a year ago. And I talked to him, and he said to me, you cannot give up. It's in Hebrew, I'm sorry. You cannot give up this thing. You have to take it. It will be okay. So I took the job immediately. An hour after he wrote me the mail, I wrote a mail to the physics coordinator of the experiment. I said that I'm very happy to accept the job. And if you read the letter, it says also, so there won't be a misunderstanding. In short, I'm very interested. In case I'm given the opportunity, I'll do the best. In short, I was appointed to be the Higgs convener. And then I asked myself, how come? When I gave up everything, I suddenly became the Higgs convener. And I remember the song of Sting, if you love somebody, set them free. If they come back to you, this means it's meant to be. So 2012 was a great year for science and personally for me as well. Because on July 4th, 2012, finally we announced, and it was so exciting, the discovery of the Higgs-like particle. How do you do it? Higgs is a needle in a haystack. I mean, there's a lot of particles that look like the Higgs. How do you know which one is the Higgs? So the thing is that you never know. And I'll explain to you, then how do you do an experiment if you never know? Imagine that this is a box, this is the collider, this jar here is a collider, and each coin is a particle. Each collision produces a particle, and the particle carries a mass, which is the number of the coin, okay, a mass. So there's a particle with a mass of 100 GeV, which is the 100 times the mass of the proton. Another particle which has the number 105, 110. So normally, in a world without the Higgs, we'll have equal numbers of each coin. You understand me? Equal numbers of coins with 100, equal numbers of coins with 105, 150, 140. If there is a Higgs boson and it has the mass of 125, say, we'll see more coins of 125. But there are so many coins that you have to make many, many collisions to start to see something. So if you make a small number of collisions and you plot the number of coins with the number that you see here, you see that more or less there are about 120, 100 coins of each mass. Nothing looks spectacular here. So the probability that there is something, the probability that we'll see what we see is normal. There's nothing special here. So now let's get more collisions. Still, we don't see anything crazy except around 125. We see that there's a little bit tower created here. Maybe there are more coins of 125, more particles with a mass of 125. What's the probability that it's normal, that we have just a statistical fluctuation, we have more than the average in 125? This is what you see in the bottom plot. So it's not so low, it can still happen. Now we increase the number of collisions to 10,000, and now you see that the tower becomes to increase around 125, and the probability that it's just a statistical fluctuation without the Higgs turns out to be something like 1 in 1,000 or 1 in 10,000, which is very low. You keep on doing it until you have 100,000 collisions on the average per each mass point, and you see a huge tower. The probability that there's not something special there, that there's no Higgs boson there, that there's no extra coins with 125, is now less than 1 to a million. When we get to a point that the probability that what we see, that the excess of particles with a mass 125, the excess is so big that the probability that there's no something special there, that it's just a statistical fluctuation of a world without the Higgs, is less than 1 in a million, then it's common in particle physics to say you have a discovery. This is translated to what we call standard deviations, and this is translated to 5 standard deviations. When we get to a peak of 5 standard deviations like you see here, we declare that we discovered a particle. And this plot can be translated now to the real thing, which is this plot here. That's the discovery plot of Atlas. You see that the probability that what we see, the fluctuation that you see in the particles with a mass 125, that we see so many particles with a mass 125 that it will not come from an extra Higgs boson, this probability is 10 to the minus 9, which means less than 1 in a trillion events will give us this. And that is translated to what we call more than 5 standard deviation. So this is why we believe that by simple counting, so physical analysis with counting, that we count too many particles with a mass 125, so many of them must be Higgs bosons. So we were very happy. I have a typo here in English. It should be Higgs Hunters Independence Day. So we decided to name the day, the day instead of United States of America Independence Day, also Higgs Hunters Independence Day, because from now on, we don't need to search for the Higgs boson because now we are Higgs analyzers. So it's our Independence Day. Now, in order to announce the result, there was a seminar. So many people, I mean, more than 1,000 people were sitting on stairs. Actually, the queue went for over a kilometer. I'll never forget it. The queue went for over a kilometer. People were waiting, even though they knew that 90% of them will not go into the hall. They were still waiting there. That was amazing. They were waiting more than one night, more than 12 hours they were waiting to get into the hall. Look at this. Everybody was waiting because they wanted to be part of history, of the announcement of the discovery of the Higgs boson. You see how they slept in the hall, just like that. And then you go into the hall. This is Mr. Higgs himself going into the seminar hall. This is Xiaolan Wu, which is what I call also a Higgs hunter. Higgs hunters are those people who for at least more than 10 years search for the Higgs boson. There are only a few like this that are really dedicating their life to Higgs hunting. It's like safari, Higgs hunting, okay? And Xiaolan Wu was so excited, she went to Mr. Higgs and told him, I was looking for you for over 20 years. And Higgs answered her, well, now you found me. And this is Higgs with François Englert, who was also one prominent physicist who actually invited the spontaneous symmetry breaking mechanism. Higgs predicted the Higgs particle, but the mechanism itself, there are many fathers to the mechanism. One of the main principal fathers is François Englert, who also a very, very, he's coming a lot to the Hebrew University here, and he's a friend of Israel. So if my grandchildren will ask, where were you at the time of the discovery? And the mistake that I made is that by changing the zoom of the picture, the circle is not on me. It should be a little bit to the right, and then you'll see me. To the right of the circle, you see me, and in the circle, you see Alex and Marumi, who is my co-convener now. So you see here me, Alex, and Marumi sitting in a row, and this is the seminar room. And the presentation was given by the Atlas spokesperson Fabiola Gianotti and the CMS spokesperson at the time joined Candela. But those people who waited the whole night, they went into the room to see the seminar and they just couldn't resist. They missed the whole seminar. And then, in summary, Fabiola says, we've observed a new boson with a mass of 125.3 at 4.9 sigma significance. And then the Higgs group made its own celebration. That's Sandra and me. We were very, very happy. And actually, I didn't stop to be happy since then still. Here you see, if you count 7 bottles of champagne, there are 7 Higgs subgroups. For each one of them, we opened a bottle of champagne to celebrate the discovery of the Higgs boson. And then came the paper of the discovery. We wrote the paper of the discovery for this magazine, Physics Letters B, which was dedicated actually to the whole discovery of the Higgs. So there was an article by CMS there, an article by Atlas, and there were 3,000 writers to this. But before I show you the 3,000 writers, we'll go one by one, of course. I want to show you that this is such an historic paper that there was this thing written at the front of the paper. The paper is called Observation of a New Particle in the Set for Standard Model Higgs Boson with the Atlas Detector, the LHC, written by the Atlas Collaboration. This paper is dedicated to the memory of our Atlas colleagues who did not live to see the full impact and significance of the contribution to the experiment, which is very moving. And I thought, doesn't it remind you somehow, died in the course of duty? So in a way, it is like that, and that's why I call it an army of Higgs. That's why I call all of us a soldier of Higgs, because these are all people who dedicated their lives to the discovery of the Higgs boson, and not all of them made it. So indeed, 3,000 names here, 3,000 signature, and this is me, just a random signature here, one soldier of Higgs, but certainly a very lucky one to be at the right job in the right time. So to complete the lecture, at that time I remember that I took Alex and we talked, and we were that's Alex Reed, my colleague, and we were talking, and then we drove Marumi to the airport, and on the way Alex looks to me and say, at the 4th of July, Eilam, is the world looks different to you today now that we completed the picture of the star model? Does it make anything to you? And I looked at him and we both said together, I remember it, the grass is greener, something like that. And then we said that it reminds us of William Blake saying, to see a world in a grain of sand and heaven in a wildflower, hold infinity in the palm of your hand and eternity in an hour. Thank you very much.
Professor Gross, thank you very much.
Thank you.
For a very moving lecture.
Thank you.
About one of the great breakthroughs of our time, and we're proud that we have you with us here tonight. And on this occasion, I would like to present you with the Oscar van Leer Annual Lecture Medal, which we award every year. And this is it, so that you can all see this medal.
Thank you.
Here it is, and you'll see it's awarded this year to Eilam Gross.
Thank you so much.
All right, here's the cover. You can even have that. I suppose we could go on for questions, but I don't think that's really.
As you like.
Does anybody have a burning desire?
Yeah, I
Yes,
see a burning
over there.
desire
Yes,
here.
sir.
In reading everything that emerged with the discovery of
Higgs.
it didn't seem like there was anything else. Nothing else emerged. Are you done?
That's a very difficult question. Hopefully not. Because even though the pieces of the puzzle are complete, if you look in the puzzle, and I did it on purpose, you see that the pieces don't really sit in place. It's obviously that we don't understand the world to the very fine, let's see if I get to that, very fine detail. And that's a crucial point, and thank you for the question. We believe that in order, here it is. Look, the pieces don't really sit together at the right place, and I did it on purpose. Because some things are still missing. We don't understand why one particle weighs 100,000 times more than the other, okay? We don't understand why there are light and heavy particles, why there are only 3 generations of particles. There are lots of missing ingredients, and we still didn't get this one law that everybody wants to get, and also Newton wanted to get it, and that was the biggest frustration of Newton in my mind. And Einstein obviously tried to look it for the rest of his life, which is the theory of everything, the one force that rules them all, that puts everything together and explains to us the hierarchy. And now we got to this point that we have one particle which is very heavy, one is very low, and everything is natural. We didn't get to this place. And if this is it, and that's it, and it might be that for many years this will be it, the physicists will remain very, very frustrated. On the other hand, there is still hope, because we have still at least 15 years of the LHC, the machine, Large Hadron Collider, to run, and we have hopes to find at least supersymmetry. There is still place for supersymmetry with this discovery. It just narrowed the phase space for looking for supersymmetry. So actually you can look at it in a positive way. It showed us where to look now. And we know where to look for supersymmetry now, or for new physics, and hopefully we'll find it. If not, let's ask the question again in 15 years.
Well, thank you very much.
Thank you.
Good. Thank you all for coming. Have a good evening.